All right, good morning. So we'll start the lecture for today. If you look at the course content, there's a couple of things that we need to discuss today. The first one being the project. So I'll give a overlook, like a high level perspective on what the project is going to be, and we'll discuss a little bit further down the line. In terms of reminders, homework 2 is due this Friday for all in-person students and next Monday for the distance learning students. In fact, homework 1 is due for distance learning students today at 8 p.m. The one thing that we have not covered yet that is there currently in homework number 2 is the idea of performance metrics. I believe that is question number 4. So we'll spend a significant amount of time today talking about that portion. But let's start off with the project. The project that we'll be working on this semester is going to be this segment anything model. Again, if you remember the syllabus itself, the course project is only going to be there, or it's 20% of the score for all the 8803 and the 8803 QF students, which is a distance learning student. So essentially, 20% of your score needs to be in this. I'll talk about like the logistics of it and the 4803 students as well if you're interested in working on the project. So what we'll be working on is this thing called the SAM model, the segment anything model. So this was released last year, April of last year. The goal is, as the title says, segment anything. Just a very quick definition of what segmentation is. Till now in course, we have only looked at something called classification, right? So if you look at the image here on the left-hand side, or the right-hand side on the screen, which is going to be the cows. So if you feed that image, a single image instead of the video, into any of the algorithms that we have seen so far, the output that you'll get is a cow. But segmentation is a little bit different. Since segmentation, what you'll have is the entire cow will be, every single pixel will be labeled. You can think of it as, okay, is this part of a cow or is this not part of a cow? Or if it's part of a sky or grass or something else. Segmentation is essentially making sure that the boundaries of a particular object are correctly defined so that you'll be able to say any pixel within that particular object or that boundary belongs to a certain class, in this case, cows. So this is a very large model that was trained last year. It was trained with about 1.1 billion segmentation masks on about 11 million images. So the goal, of course, is that we cannot recreate this. It's highly impossible to train a model like this for us, but it allows us to do a couple of things which can be very beneficial from this course perspective. Because one of the things that we'll be discussing throughout the course is the cooperation between human beings and the machine learning models. So what this allows us is this idea of two different inputs, one of which is the image itself and the another one is the prompt. So I don't know how visible this image here is, but it's basically two cats, and if I click or point at a particular cat, in this case I'm doing it for the right hand cat over here, then what is going to be segmented is just that particular cat. I hope you can see that. There are two cats here. If this were a classification algorithm, the output is going to be cats, that's it. But since it's a segmentation algorithm, it would have segmented cats. But now what we can do further as human beings is we can prompt it. This is something called as visual prompting. Now you would have heard of the word prompting from let's say ChatGPT or something, but that is more text prompting. This here is visual prompting, where we point and click on top of a cat, and what happens is that cat is going to be segmented here, compared to, let's say, all the cats are segmented and so on. So this is a nice way of thinking about how machine learning models and human beings can work together, essentially, in order to give you what you want. So this paper worked, I believe they did it on like 15 data sets or something, where the 11 million images are collected from all these data sets, and ideally it is supposed to work on anything, and that's why the word segment anything model, which they came up with, is that, you know, it has to work on anything. But and there can be some very important contributions from this, right? So one of the biggest problems that we are facing in the autonomous vehicle industry is just the labeling portion. There's this data set called Cityscapes, where for every image to do segmentation, it takes a human being about 90 minutes to complete the segmentation, to get these kind of masks out of it. Maybe if we had these kind of segment anything models or a better version of these models, this 90 minutes can be, hopefully can be brought down to a much smaller one, let's say 15 minutes or 10 minutes, where the cooperation between a human being and a machine learning model can help you label the data and so on. So there can be very nice real world implications for having these kind of models. The problem, however, is that it does not work very well on all data. So in the previous case, if it works on, let's say, pristine, good-looking data with all, you know, the head-on vision, ego camera from your autonomous vehicles, but as soon as you bring in something like a fisheye camera, it does not work out as well. So this is the ground truth you see here on the top, while at the bottom is the segment anything model, the output from your segment anything model. And some of the important characteristics are not segmented. That is the pedestrians who are smaller than, let's say, a certain number of pixels and so on. So this is, it's not an easy problem, and same thing happens in medical domain as well. Ideally, again, segment anything means that you should be able to locate all nodules, let's say, that are present in the lungs or any kind of cancer cells or any other problematic parts that are there in a medical image that is not healthy. But in many cases, it's not possible to segment them quite easily. A model is not able to do it because it has not learned on top of it. Because one thing we have learned, at least till this point in machine learning, is that you require this kind of training data. And since your model learns on training data, hopefully whatever you're giving a test output on is going to be similar to that training distribution. But sometimes it's not possible, hence your models fail, especially in these kind of real world scenarios in like medical domains and the fisheye camera settings. Also in seismic settings as well. In this case, this is a seismic image. There's a fault. I don't know how visible it is, but there is a fault over here, activity of an earthquake. A network basically thinks, the SAM model essentially thinks that that is a distinction, that is a boundary between two objects. And that's why you see that there is this kind of a boundary. It's thinking a fault is the boundary of an object in this case. Now, the goal for us, again, this is a very big problem, right? For us, this is a fundamentals course. This is not going to be, we're not going to dig too much deep into these billion parameter models. For us, what we'll be very interested in is this idea of what manual prompting is and how that helps us. In this case, for instance, if you have this entire image, you can get two kinds of outputs. If you don't give any prompts, this is how the results is going to look like. And this is from Meta's website. So you can go through their website, and they have a few select images on top of which you can try this. And you'll see that it usually works very well. And then if also you add these kind of prompts, hopefully you can see the points over here, then that means that only a few of these prompts, few of these vegetables are going to be segmented in this case. So this is essentially what we are looking for within the project. This is what we'll call manual prompting. And the reason manual prompting can be good and what we'll be looking at is because it will help us. So before you saw that there was this kind of a, let me try to find my cursor. Okay, there was this kind of a boundary between objects, right? But now when you have prompts, when you say, I want my model to include certain points, and that is given by the green points, and then I want to also exclude certain points, which is given by the red points, I'll get my region of interest without having that boundary. So by having human beings go through and click or put bounding boxes on top of the data they're looking at, you should be able to find these regions of interest. You should be able to segment these regions of interest using your SAM model. And we can do this in a iterative fashion. And this is where the learning comes in. So let's say I have my input image over here. My input prompts are going to be these kind of green prompt, which is what we would call an inclusion prompt. That is, I'm telling my model to include this part of the image, and the red prompt is going to be exclude this part of the image from your segmentation. And this is how my result is going to look like. Ideally, I wanted this yellow target segment. This is what I wanted. But based on these two prompts, you see that only this part of the segmentation mask is there. Then you can go back, and since you have learned something about this model, about the prompts, you can now say that I want to have a couple more prompts. I'll have another green prompt here and a red prompt at this region. which tells you that, okay, I now need to, which tells the model that it needs to correct itself. It learns essentially that it needs to take this into consideration, this part as well within segmentation mask, and that is what you see here in this model. So this kind of adding prompts is sort of a learning phenomena, which we will discuss later, sometime during March, essentially. So in terms of the project itself and logistics, so the goal, increases zero-shot capability of SAM based on prompting. So let me just quickly say what zero-shot capability is. If your deep learning model is something that you are training and retraining on, then we call that fine-tuning, essentially. We call that retraining or fine-tuning. But if you want to take a model out of the box, someone has put their code online, which Meta has done for SAM, and try it on your own application, then we are going to call it zero-shot capabilities. We are going to assess the capabilities of that and say it is zero-shot, and we want to do that in the course project. We don't want to retrain image encoder, because that, again, these billion parameter models, will be very hard to retrain all these things. But rather what we can do is have prompt encoders. So the prompt encoders are very simple architectures. It's much simpler than image encoders, because all you're looking at is either bounding boxes or points. So we'll take these prompt encoders and we'll fine-tune or replace them, or you would have to fine-tune or replace them, and then analyze the human prompts also kind of systematically. I'll probably in the next week, we'll have more in-depth discussions about what this means. So one of the TAs is currently working on creating like a 2 to 3 page document where the exact details of what you'll be doing, we'll send it out. But I just want to talk about the logistics very quickly, which is that you'll be working in groups of 3. And this is specifically for 8803 and 8803 QF, which is the distance learning students and all the grad students in person here. So you would have to create a team of a group of 3, essentially, to work on this. You should have the link. The file is online. The lecture file is online. So let me go there, have it open. So all you would have to do is just form groups of 3 and just fill in. So essentially your names, section, GTIDs, that's it. So the red is for us. We will, looking at the number of people who have signed, or the number of teams that have signed up, we'll actually give you data sets. We'll give you different data sets, all vision data sets. It could be medical, natural images, seismic data sets, and all these things, so that you'll be able to work on top of it. The project is not going to be like a competition based. So it's not like, one team is getting 0.54, the other team is getting 0.55, they'll win. No, it's not based on that. Everybody is going to have an equal opportunity to get your entire points. What we'll be looking at is not just the score, the evaluation itself, but the novelty, the idea that you bring in, the philosophy that you bring in into the methodology and the project itself. So it's not going to be a we're not going to have like any competition website or anything like that. You should have access to this, so please try to fill this by Wednesday. So that is going to give us enough time to discuss, okay, the TAs and I, it's going to give us enough time to discuss about the number of teams there are and put in the data sets and other stuff. Yes, question?
So is 4803 included in that?
I'll talk about that in a little bit. The question is about 4803, so I'll talk about that in a little bit. So let's talk about the logistics of it. So in the beginning, when we had discussed in the syllabus, if you look at it, it's going to be for the 8803 and the distance learning students, the points are going to be like 40% homework, 10% exam 1, 10% exam 2, and 20% project and 20% for the final exams. So you will have the option of choosing, instead of doing an exam, the final exam, you will have the option of having a 40% project. So in that sense, it'll be more like a traditional grad course. Most of the grad courses, if you see, it is like this. Your final exam won't be there. Instead, you will have a project which is going to be similar. Now, the expectations of a 20% versus 40% is going to be different. We lay that out very clearly once we have all the teams decided. And you don't have to decide this right now. Ideally, your progress report is going to be due on March 8th. So in the progress report, you have to indicate whether you want to have a final exam or you want to choose a project option. There's a couple, if you choose a project option, I think you can see the course content, but it ends on April 21st. That is, you should give your report on the 21st of April, and that'll be it. So there'll be no exam. So that'll be the end of the course, essentially. And I believe it's before the reading period. So if you have a couple of exams, it does not clash. So that's one good thing. Irrespective of whether you choose to attend the finals or not, you will still have to have this kind of a progress report, a final report, and a 5-minute presentation video. Again, when we give that 2 to 3 page document, once the teams are finalized, you will have, you can see essentially the timeline as well as the requirements. Any questions? Yes?
Can you show the previous slide?
Any questions here or? Again, you don't have to make a decision now. Once you see the exact specifications on the project, you can make a decision about the 20% or 40% later. So this is for grad students. For undergrads as well, you'll have the opportunity to work on the project, but I'm a bit undecided on the logistics of it. It'll depend on the interest shown by and the number of people who will be doing it. So ideally, there can be a couple of ways we can do this. Either you can use a project as something of a bonus points, or you can do the same thing, which is, in your case, I believe the breakdown is 60% for homeworks and 10% for the 2 midterms and 20% for the final exam. So you can say that you can replace your final exam with the project itself, which will be the 20% option, or you can take the final exam and use a project more as a bonus, essentially. So if you've missed any homework or you're not getting full points on the homework, you can use that as a way to make it up. But again, this is going to depend on the interest shown. So what I suggest is that you can email me, basically saying that, one, you're interested in the project and what you want to do, essentially, which is the last 2 options here. You can choose to use it as bonus points, or you can use 20% instead of the final exam within the project itself. Again, you don't have to make a decision now. In fact, for you, I think for the 4803 students, there's going to be a lot more time. You can take until after the first exam is done to see how the exams are being played out, how comfortable you are with the examination module, or if you want to do the project module. Either is going to be fine. But until that point, just email me so that I can gauge some interest. If it's just 2-3 people who are interested, then we can completely personalize it. If one person wants bonus, we can do that. If 2 others want to replace the exam, we can do that for them. But if there's more people who are interested, then maybe we have to do some standardized something. So just email me your interest, whether you want to work on the project or you want to work on the exams. Either is fine. Any questions for 4803 students? Again, the expectations will be communicated about what the 20% versus 40% means. We'll also have this kind of individual contribution. So you don't have to worry from now itself, whether while forming teams, whether you want to make it 40%, 20%, or if you're an undergrad, if you want to take the final exam or not. You need to create a statement on individual contributions that we'll be using in order to assign points in this system. So the link should be available to everyone. It's in the slides. I think that should be fine. You should be able to click on it, or at least copy paste it onto your browser and fill in the thing. Just for all the 8803 and distance learning students, please try to do this by Wednesday. That will give us a couple more days to look through the logistics and give you the thing. So what we'll be giving you, by the way, is the SAM module, and we have this framework. We are currently working on this framework where, based on the SAM module, we are creating a framework for you to do the prompting and go through this, let's say, fine-tuning strategy based on the human prompting itself, and you'll have access to this. The reason it's not out now is because we want to know the number of data sets that we'll be doing, so the number of teams there are. Each team will have their own data set, so what we will do is we need to alter the code a little bit so that it is viable for all these data sets. We want to know the number of data sets. So by Wednesday, if everybody can sign up, then after that point, by Friday, we'll release the data set and the SAM model and the personalized framework as well. Any questions about the project before we move on? Yes.
We have the option of either just going with just the exam, or we can also do the project and have it as extra credit or something like that, right?
Yeah.
Okay.
As I said, I'm still undecided on the logistics. Depending on interest, gauging the interest, we can have either of the two things you mentioned, or maybe if there's anything else, that's fine as well. Yeah, so for 4803, that is how the current syllabus is. So it's 60% homework, 10% first midterm, 10% second midterm, and 20% for the finals. So you don't have to worry about project at all for the 4803, which is the default case. If you want to do the project, if you're interested, then you can email me about the. Yeah. Yes. I'm sorry, I can't hear you. So what time you want to email me by? Okay, so so I think I've written here, right? So if you can email me by the end of this week, it'll be good, but it's not a commitment. I'll give you an option somewhere at the middle of March as well, to see if you want either of the two options, or if there's any other option that is there. So for 4803 students, the default is no project. So if you want to do a project, just email me so that we can put you into teams as well right now, so that you can start. But there is no commitment whatsoever for 4803 that if you email, you have to pursue this path or not. In the beginning, it's just for us to create the teams and know the number of data sets that we need to provide everyone. That's it. So if by end of the week you can email me, that'll be perfect. Yeah. Yes. Yeah.
Database. If you're Facebook and you train this model with 1 billion different images,
yeah,
why do you give it out for free?
That's a good question. I think machine learning and academia works on this principle of, this is a very idealized view, but a rising tide lifts all boats. So that has been the policy for the last few years, especially since deep learning came out. And more importantly, there might be security things as well, where 11 million images, 1.1 billion images doesn't, there is, I don't know how to say this, like it might not belong to Facebook. Those images themselves might not belong to Facebook. They might belong to the community. So it is a good idea to release these models to everyone. So they release these models for us, but I'm absolutely certain they have multiple other modules within. For instance, in classification, the most prevalent data set out there has about 1 million images with 1,000 classes. But I know for a fact that Facebook has one with like 50,000 classes in their internal thing. So they will have better models, and they will keep on learning these better models. So, and also, of course, that more open source any code is, more research will go into that from academia and from other people as well. Any other questions about the project? All right, so last week we ended with artificial neural networks, or I don't know if ended is the right word, but we essentially looked at backpropagation, and we stopped at backpropagation. So this is more of a kind of a comparison between everything. We usually see this. So assumptions of feature distance, we didn't make any assumptions on feature distance at all with the neural networks. Feature normalization, as in any other machine learning module, we do require this kind of a feature normalization. Cost function, ideally you want it to be a convex cost function, but there are ways that you can make it work with non-convex functions as well, neural networks. We won't discuss those methodologies. That is more of an optimization course. We do require an additional term for regularization, and we'll talk about what that regularization is in a bit. So it is a nonlinear classifier. So we saw specifically how multiple hidden layers and having activation functions creates this kind of a nonlinearity. We do have a probabilistic view of prediction. It could be a generative or discriminative model. We didn't discuss that yet. Again, we'll look back on neural networks somewhere in middle of February and go into a more deep learning perspective. And there we'll have access to these kind of ideas of discriminative and generative perspectives. So it is a parametric model. You have your W, you have your B, so it's always going to be a parametric model that you're going to learn from. And with many layers, there is going to be overfitting. Now, every single time we have looked at this slide, I've mentioned that we'll talk about overfitting in a little bit. Today, we'll discuss about what exactly overfitting is, at least in this context. So this is more of a summary from backpropagation last time. Again, think of backpropagation as a very greedy algorithm. It's going to take the error that is present at the very end and use all possible error to update the weights W. The method backpropagation does not care that there is a V, there is a U that is behind these layers. All the error it has access to, it will use it in order to update your W parameters. It could be a very simple gradient descent algorithm, which is this kind of a W t plus 1 equals W of t minus alpha dou E by dou W for this particular weights. You take that error, all the error you have, update your weights. Now look at how H is changing. And look at that change in H, and now update V, which is exactly what this one is doing here. Dou E by dou G is equal to sigma HI 1 minus HI Vij dou E by dou H, right? So you're just backpropagating layer by layer. You're looking at the changes that needs to happen and updating the weights. You don't care about what happened before. You don't care about what happened after. At that particular layer, all the error that you have access to, it'll be used in order to update your weights. So it's a greedy layer-wise way of trying to obtain these kind of weight changes, weight updates, weight and bias updates. So that is more of from a training perspective. In inference, what happens is that it's just a forward propagation. So given some kind of raw sample, we pass it through all the hidden layers from the input layer, hidden layers, and we get certain output. And usually when we think of output layer, what we have here is what we're going to call as logits. So the output of any neural network, we're going to call them as logits. And in this case, it could be some kind of raw logits like 3.2, 5.1, minus 1.7. So in this case, I know there's like only 2 nodes that are shown, but if there were 3, this is what, let's say, an sample output can look like. So what we're going to do getting these raw logits is we're going to transform them into a probability. And that probability is given by a softmax function. So this is what a softmax function is going to look like. Exponent of Yij given by the sum of all these exponents is what a softmax function is. So this is a way of converting any given raw numbers into a probability distribution. So 3.2 is going to be converted into, let's say, 0.13. 5.1 is 0.87, and minus 1.7 is going to be converted to 0. So what you have here is now a probability distribution rather than a simple set of logits. So this is one way of looking at and thinking, okay, this sample xi belongs to y2 with 87% confidence. That is how you can interpret an output, something like this. And that's why in that summary table, we had a probabilistic view and yes in that statement, because once we get all these logits, the sigma W transpose, in this case, maybe H2 plus B, once you have access to all those outputs, you put a simple softmax activation on top of it, convert it into a probability distribution, and then you can say that the current sample that you have is 87%, with 87 probability, you can say that it belongs to class 2. So this is essentially what happens at inference. More of a summary regarding the training itself. Usually during training, what we do when we get this output is we give we're going to call this a one-hot ground truth label. In other words, we're going to backpropagate a vector, and it'll be 1 at the point where we want the output to be maximum. So in this case, the network said that the sample is class 2. But maybe that's incorrect. Maybe the sample was actually from class 1. So what we do at that point is say, you're incorrect, and we backpropagate this vector where the number 1 is going to be at the location in which we want the class to be in. So in this case, it's going to be 1, 0, 0, and we backpropagate it. And there's a loss function to obtain error between them. A very simple loss function, of course, is just a simple subtraction, in which case it's going to be 0.87. In this case, it's going to be 0.87.13. So 1 minus 0.13 and 0 minus 0.87, right? So it's just a very simple error that we can take and then continue backpropagation. This is essentially how you do the exact math of if you were to code backpropagation, for instance, you would have to backpropagate this kind of a one-hot ground truth. Again, that would also depend on the loss function that you're using, but thematically, this is the way you would backpropagate a loss function. So let's look at that from an image classification perspective, what that would look like. So ideally, in the beginning, in the 90s, for instance, when neural networks were getting quite big, the first thing that they showed very good promise in was in classification of images. MNIST dataset, which is a set of numbers. I think we saw that back in lecture number 2 and lecture number 1, which is just a set of numbers. Postal code, people had written numbers to send posts. People took that photographs. I think there's about 60,000 images in the training set, and people try to classify, researchers try to classify those images based on these kind of neural networks, multiple hidden layers neural networks. And it saw, we had perceptrons back in the 60s. There was a huge problem with it, which is XOR problem. And once that was solved, we have multiple hidden layers. In 1980s, backpropagation came into existence, and 1990s, it had a bigger surge essentially because of access to large data sets. We knew that we have to classify larger data sets, and that's when neural networks got a different kind of a boost. So that was for image classification. If we think of what a neural network does in this case, so you can think of y cap as your outputs that you need. X W transpose plus B is still the same thing that you had before. Sorry, this should have been W transpose X plus B based on the usual thing we do, but we have taken a transpose across everything, and this would be correct as well. So essentially, you'll have your data set X. Your W transpose and B are the weights and bias terms that we always have, and you'll have some activation function that is phi. So you can still think of an image classification problem in this, except the difference is your X. X is the only difference, where instead of thinking of it as a feature vector of, let's say, 5 or 6 features, you take your image and convert it into, your pixels are now the features. So you take an image, you convert it into a vector. So if you have so for MNIST dataset, for instance, each image is 28 cross 28. So your vector is now a 784 cross 1 vector. 28 multiplied by 28, which gives you 784. So 784 cross 1 vector is the input into your model. That means that the number of nodes that we need to start off with is going to be 784, right? And 28 cross 28 image is very small. In fact, when you look at it on a screen, it's very hard to even say what that number is going to be. The usual images that we see, HD images, 1080p, it's much, much higher. So if you think that you need to convert that into a vector and put it in, there's going to be millions of parameters even in the first layer itself, which is very hard to create these kind of deep networks. So somewhere in the middle of the course in February, we'll discuss about something called convolution, about the idea of using convolution within neural networks. And these kind of linear functions, they won't be sufficient for us in terms of neural networks. The idea is this, yes, as I mentioned, so we take an image, we stretch the pixels into a single column vector. So for input 32 cross 32, it's going to be 32 cross 32 cross 3. I'm not really sure how much that is. I know 28 cross 28, MNIST is very well known. I know that's 784, but 32 into 32 into 3 is going to be much more. The number of, the size of your vector is going to be much more. So think of how this is going to scale. It's very difficult to scale something like this to large scale images and creating networks. And the idea, the motivation here is that we need a different kind of classifier. Maybe within neural networks, but other operations need to happen within this in order to help us solve these kind of large scale problems. So MNIST dataset, 28 cross 28. Cypher10 dataset, which is also a very popular dataset, is 32 cross 32, but it's color images. So it's 32 cross 32 cross 3. So there's an RG and a B channel, while MNIST dataset is a grayscale image. So it's just a 28 cross 28 image. All right, so there's a few terminologies that we use throughout neural networks, and we'll be using sometime in regression and clustering as well. So let's start with one of them. The first one is batch size. So we talk about, so in segment anything, right? I talked about 11 million images with 1.1 billion masks. So think about what gradient descent is going to look like in those kind of models. If I want to create gradients for 1.1 billion masks, the amount of computational resources I need it's impossible even for Meta and even for these kind of, for any other companies. So there's a trick that people use, and that is that they convert all your data into a certain set of batches. So let's say if I have a million images to start with, I'm going to say that I have about 10,000 batches, and in those 10,000 batches, I'll have 1,000 images each. I hope that math works out. But essentially, that means that each batch will have about 1,000 images, and there's going to be 10,000 of these batches that is going to exist. And I can use that in order to create a machine learning algorithm where I can use backpropagation, not on the entire million images at once, but on just 1,000 images. Get those gradients, update your model. Again, backpropagation is very greedy algorithm. All it is looking at is at a single instance what that gradient is, and it's going to update its weight as much as possible. So in a single batch, you get your gradients, you update your weights. Take the next batch, update your weights again. Take the next batch, update your weights again, and keep doing it until you finish all your million images. And once you finish all your million images, this is what we call an epoch, or what we will call an epoch. So until this point, we just use the word iteration very loosely. So every single gradient descent has an iteration where at a single iteration, your weights are updated. But since now you have access to batches, that means that there's going to be 1,000 different or 10,000 different batches where you're going to have different gradients, right? So an epoch is when all the million images, all the batches, you get the gradients and update the weights. That is how you're going to define what an epoch is going to be. Does that make sense? Any questions in terms of batch size and epochs? The word round, the third one here, is a little bit more, there's no simple and good definition of round. It's essentially used more colloquially rather than technically. In this class, the way we are going to be using it is the model, if it goes through a feed forward and a back propagation, then you have completed a round. The next one is very interesting, and this is something that you're looking at in the homework right now as well, which is the idea of validation set versus something called training set versus something called a testing set. So we have data, let's say, MNIST data set, which has about, if I go back to that slide, we said something about 60,000 images in the training samples, and we have something else called test samples with 10,000 images. Now, we have never clearly defined what the definition of training samples and test samples is, right? So the way we are going to define this is by saying that anything that we can use during training is going to be our training samples. Very clearly, if we have 60,000 images, then we can use all these 60,000 images. We can use the labels of these 60,000 images in order to train our algorithm. But what we want to do is make sure that the machine learning algorithm has not learned some kind of a memorization function. So it hasn't just memorized that the third number here is, let's say, a 0. A fifth number is 2, or so on, right? We don't want it to memorize all the data it has seen. And it will have the capability, because if we keep on increasing the number of hidden layers, keep on increasing the number of neurons, number of parameters there are to memorize your data is a lot. So it'll be very easy for an algorithm to memorize and get and learn all the data. You don't want that to happen. That's why we keep out these 10,000 images to test your algorithm at the very end. We say that about this 10,000 images, and you want to have a performance that is good on these 10,000 images. So whenever we report the output of a machine learning model, we don't look at how good it did in the training set. We want it to do good in the test set. and that's why the goal is machine learning, right? So it needs to learn some underlying functions about the data itself, rather than just memorizing what that data class is. So that is about like training and test samples. But there's also something else called validation dataset. The reason validation dataset exists is because of what we talked about in the first summary slide, which is the idea of overfitting. Now, the idea of overfitting is going to make more sense when we talk about regression during next class. But in this case, I'll just give a very simple idea of what overfitting is. Let's say I have access to certain data points. So let's say it's circle. This is supposed to be circle, but I guess it's coming out as a square. It's fine. So let's say I have these data points here, and I have X data points. Overfitting is when you learn a classifier that completely memorizes and fits to the training distribution. So all this is from training data. So let's say I have my output, my classifier is something like this. So if my classifier has, we say that this particular classifier has overfit to the data because it has not learned the individual characteristics of the data points in order to make the classification. Rather, it has overfit to the data, the training data itself. It has almost memorized the training data in a way that it now creates a representation space, a kernel, if you will, which we did during SVM, and it has gone into this kernel space where each and every data point is accurately and precisely described. So in this case, the classifier is getting 100% classification, where the square modules and are to the one side and the X modules are to the other. But it's not really learned it. It hasn't learned the basis function for the data itself. Rather, what it has done, it has memorized this entire data in a particular representation space. It could be in a kernel, or it could be in a hidden layer. So in this case, it has overfit. A network has not been given, or it has been given too much leeway, essentially, to get to 100% confidence without actually learning anything about the data itself. It has memorized, essentially. When we come to regression, we'll have a more concise representation, a more mathematical representation of what overfitting is. But essentially, it means that you're getting 100% accuracy on your training set, but as soon as you come to your test set, you don't get that accuracy because your classifier has overfit to your training set only. To make sure that this does not happen, we have something called a validation set. What we do with the validation set is, instead of having 60,000 images, if I go back to my MNIST, instead of having 60,000 images in my training set, I'm going to take a small amount out of it. I'm going to say that 50,000 I'm going to use for training, and about 10,000 for something called validation. In other words, what I do is, at the end of every epoch, I treat the 10,000 images as a test set. I look at my validation loss. I look at how my model is performing on the 10,000 images of validation set while updating the weights on the 50,000 images in the training set itself. So in other words, the validation set is not used for updating the gradients. It's not used for learning the module. Rather, what it is used for is just looking at the loss. It's looking at the accuracy on the 10,000 images in the validation set, and you can use that to select the best model. So let's say at the end of epoch 25, I have my training accuracy as 96%, while my validation accuracy is like 75%. But at the end of epoch, at the end of epoch 26, I'll have my training accuracy to be 98%, but my validation set is now, the accuracy on that is 73%, right? So my training accuracy has increased, but my validation accuracy has decreased. This means that the figure went away. This means that on my training dataset, my model has overfit. Because its training accuracy in the training set is increasing, while in my validation set, the accuracy has decreased from 75% to 73%. That means that it has overfit, or it has memorized everything in the training data without actually learning anything that you can now see in the validation set. Yes, question?
Some of the pictures.
Which one?
The two data sets.
the x and square. Oh, this one.
Yeah.
Yeah.
What exactly do you mean by classes?
Oh, classes is the output label, sorry. So if I have, in this case, 0 to 9, that means that there are 10 labels. So whenever I say use the word classes, it's actually the y, which is the labels.
So for that one as well, it's just like 10 different pictures for the bottom one?
Yeah, the bottom one as well. I don't know how easy it is to see it, but the first one is airplane, second one is car, third one, it's hard for me to see as well. It's a bird, I guess. Yeah, it's birds, so on.
Thanks.
Yeah. So validation subset is essentially at the end of every epoch, we look at the accuracy on the validation set and use it to select. So let's say I train for 100 epochs. I'm not going to just train until the end of 100 epochs and select the model after 100 epochs. What I do is I keep account of the validation at the end of every single epoch. At the end of epoch 1, maybe my validation accuracy is 20%. At the end of epoch 2, it may be 22%, so on. Let's say around 70th epoch, your validation accuracy is not going to increase above a certain threshold. That means that everything that you're doing is just overfitting to your training set. It's not really helping you with increasing the learning part of the model. Rather, from that point on, it has just overfit. So that's one way of saying that, okay, I've finished 100 epochs, I've finished 100 times training and updating my algorithm. Maybe at this time is when I stop training it. Maybe at this point, at let's say 70th epoch, I just start using it for inference. I stop the training procedure there. So that's one way of thinking about how many epochs there can be within a neural network training algorithm. So that is the validation set. Usually, and you are looking at this as well in homework number 2. We have this kind of a validation, test, and training split that we are using. Actually, I don't know if the validation was there. I need to check that again. But essentially, you're using the training and test set. We are doing a split based on a seed in order to get exact number of training and test split, and using that for the question number 2 and from there on. Next important part is the idea of learning curves. Again, this is also something that you're seeing within the homework itself. It basically shows us how the training and validation score compare against a size of the either the training size or essentially the epochs. So I think this is a better place to talk about learning curves themselves. So look at the 2 things at the bottom. So this is essentially what I was saying before, but instead of looking at it in terms of the number of epochs, you can also look at it as the size of the data set. So in MNIST data set, we have 60,000 images, but in, let's say, something like ImageNet, there's 1 million images. Maybe there's a point somewhere at 200,000 images where even when you increase the number of images in your training set, nothing is happening. Your model is not learning anything new because everything it has already learned, everything it needs to know is there in that 200,000 images. Now, selecting those 200,000 images is a different question. It's another research topic called active learning, but the way we know that it has overfit is by looking at this curve. Okay, so at this point, your training set size, let's say, is 50,000 images here, while it's about 100,000 images here. Even with the increase, your error is not decreasing. I was talking about accuracy before. Your 20% increases to 95%, and so on. In this, we are talking about error, which is looking at 5% error, 10% error, 20% error, and so on. With the increase, ideally, you want a decrease in your error or an increase in your accuracy. You can think of them as opposite to each other. And your output or your model becomes better and better until a certain point. At this point, your model has learned everything that it needs to learn. So after that point, there's nothing more to learn, essentially. So even if you increase this training set size, there's nothing more that you can do. Is that clear? Yes.
Why is the error increasing as the training set size increases for the training set?
In this case, I think this is incorrect. So I need to redo this graph on the left-hand side. this probably would have been accuracy, this would have made more sense if it were accuracy. So error is on the right hand side, that is correct. So that is more from a learning curve perspective. It gives us an idea about how a model is training. So in homework, when you're doing the homework, you'll essentially see that the accuracy keeps on increasing, or some performance metric keeps on increasing. In this case, I really don't think that there's anything, you'll see a lot of overfitting. You can change the regularization term and see what is happening in your SVM module or in your logistic regression module as well. If you change the regularization, if you make it very low, then that means that overfitting happens faster, happens easier. We'll discuss that more about overfitting in the regression module, which is going to be from next class onwards. But you can think of that. You can use that within a classification setting as well in order to see how overfitting works. And the way we can visually see it is by having these kind of learning curves. The next one is cross-validation. This is another terminology that we'll be using quite a bit. So what is cross-validation? So let's say that I have access to these 50,000 images, 60,000 images. Let's say I'm not giving you a train test and test set separately. I've just collected about 60,000 images and I've given it to you. Now, one person might say that I'm going to choose this 10,000 images as my test set and train on the remaining 50,000, and I'll show you results on this particular 10,000 images. Another person might not do that. Another person might choose some other kind of 10,000 images. The first person chooses the first 10,000, second person chooses the last 10,000. Right? So in this case, the output is going to be different. The model that is learned by two people is going to be very different from each other. And the question then becomes who to trust more, because till now the way we have, let's say, compared the two models is by looking at the validation accuracy, right, or the validation error. Whichever has a higher accuracy or a lower error, I'm going to use that person's model. But since both of their validation and test set is going to be different, it's very hard for me to compare which is better, whether one is better than the other. The best way to solve this is by randomizing the process. So we say that each person needs to do it 10 times. They have to take a random number of 10,000 images in their test set and the remaining 50,000 images in their training set. Train the model on the 50,000 images, give me the result on the 10,000 images. Next, repeat the process again. Randomize it. Randomly select some other 10,000 images within the entire data set, within the entire 60,000 images, in order to create a new trained test set and give me the result. So that's why we have these seeds, random seeds and stuff within the framework that you're seeing within the homeworks, where we can create any different kind of combination of images. We can take those combination of images and use them as a test set and use them as the train set. This way, if you do it, and this is called cross-validation. Essentially, you're splitting your data set into multiple different test sets and train sets. You're training on those models and giving me the results. The left-hand side is a very simple validation split versus the right-hand side is a more of a cross-validation split, where I can take, I know this is written, or the thing makes it seem, the image makes it seem like the first few images will be the validation set in seed 1, next few images will be validation set in seed 2, and so on. But usually it's a randomization process. I can choose any images within this the entire available data set to create the first validation setup. Then I can use any images within the 60,000 images to create the second validation setup, and so on. So this gives us access to something called cross-validation, and we call it like 5-fold cross-validation or 3-fold cross-validation, where the number of times we are doing this randomization process and learning the model again and again is the n-fold or k-fold cross-validation process. Is this, yes?
Parameters.
I'll discuss hyperparameters in the next slide. But essentially, we'll have, I just said k-fold, right? K is, how do you define what k is? Maybe it's 5, maybe it's 3, maybe it's 10. So anything that can be set by human beings or the engineers, any decisions that are taken by human engineers is what would be a hyperparameter. It's not a parameter. Whenever we say a parameter, it's theta, it's w or a b. But hyperparameter is something that is not learned, that is set by us. We can set learning rates. We can set these k, for instance. So that is what a hyperparameter is. Yes.
What do you mean by the model sees this data during training, never learns directly from it?
I'm sorry, could you repeat that?
The second bullet point under validation.
Yes, the model sees this data during the training but never learns directly from it. Okay, so the question is what that sentence means. So we talked about 60,000 images in MNIST, which is a training set, 10,000 is test set, right? So within the 60,000 images in the training set, we further divide it into two parts, which is the training block and the validation block. Training block, let's say I'm going to keep 50,000 images and 10,000 images in my validation set. I'm going to use the 50,000 images in training in order to update my weights. So it is going to see, the model will see the 50,000 images, it will see the outputs, it will have access to gradients, and it will use those gradients for updation. But it will not use the 10,000 images for updating the weights. That is what we call a validation set. So we do that because we don't want it to overfit within the framework. So that's why at the end of epoch 1, we have access to 60,000 training images, out of which 50,000 I'll use it for training, the next 10,000 I'll use it for validation. Same thing, I'll do it for epoch 2 and so on. And at epoch 70, I'll realize that my training accuracy is increasing, but the results on the 10,000 images will now be sufficient, will now be the same. So from 70 epoch to 100 epoch, it is going to remain the same. So I really don't need to continue doing the training, or I could use it for model selection. So at 70th epoch, maybe my validation accuracy was 75%, while at the end of 100 epochs, it has overfit and the validation accuracy has gone down. So it's now 60%. So that means that you shouldn't take the 100 epoch model, but rather take the 70th epoch model. So that sentence is just saying that the validation set is not learned from the, the model parameters are not learned from the validation set. Yes?
Is cross-validation used to compare two different types of models to each other, or is it used to optimize the training set for a specific model?
The second one. So the question is why cross-validation is used. I think when I said the comparison, it was more of a way to motivate based on what we were looking at in the homeworks. But ideally, the second thing that you mentioned is why we use it most of the time. Cross-validation is used because we don't have access to the test. Many times we don't have access to test set. We don't know what a test set is going to be. In that case, we want to choose the best possible model, so it is going to be used for choosing that model. Yeah. Yes.
So you mentioned five-fold cross-validation, right?
Yeah.
So is it necessary that if it's five-fold, for example, the val will be like 20%, or if it's seven-fold, then that will
so the question is, how do we divide the cross-validation, the split, essentially? So typically 20-30% split. Is it going to be dependent on the K value, which is your cross-validation, if it's a 5 or 7? Usually no. Because ideally the reason we are doing this 5-fold or 10-fold cross-validation is because we want to select the best possible model among the 10. So the ideal thing is an infinite, an n-fold model, right? So in that case, you don't actually need access to the 20-30 or any kind of a split. So generally, it's not used as a framework for selecting the K. Any questions? Any other questions? All right, so in terms of learning curves, we talked about this a little bit before, but we can use this for not just looking at your accuracy or error, but also you can start, this is the procedure essentially. So you can set aside some kind of validation set. I'm just saying 20 samples here, but this is the 10,000 we were discussing before. From K equals 1 to N minus V, because N, let's say, was you have a total of, in this case, we have about 100 samples. So that means now we only have about 80 samples in our training set, right? We take the first K samples within our training data set, and we start fitting the model. We create this model based on just these 80 samples, and we evaluate it on the validation set. And again, this is within a single epoch. So within a single epoch and within a single validation, within a single fold of the cross-validation. And then we retrain the training score and evaluation score and discard the model. So not retrain, but retain in order to create the learning curve. But again, two things are happening here. One is the epoch itself, and another one is the cross-validation part, where based on the 80 samples, we pass it through a model. we look at what the output is, and we update the model based on the 80 samples. Next 20 samples are only used for just the validation part. Again, this is still part of the training set, not part of the test set. The 20 samples are used as part of the validation set. And in many cases, when you don't have access to test set, you can use this as your training procedure. Since you'll have an 80-20 split, for instance, you can do a 10-time cross-validation process and say that for across the data sets, across the randomized data sets I've chosen, this will be the best possible model that I can choose. So the two things happening, which is the validation set itself and the cross-validation, which is K. Any questions? Yes.
Ever not have a testing data set? Like, couldn't you just take a few of your training out?
The question is, why wouldn't you have a test set ever? The answer for that is that many times, right, you're given 100,000 images to start with. If you are given 100,000 images and someone else was given 100,000 images to create the model, then maybe you are going to choose a different set of 10,000 images for testing, or that person will choose another 10,000 testing, or I would have had to give you 90,000, the other person 90,000, and use the other 10,000 and tell you that this would be the test set. In many cases, it's highly difficult to do it because data, we are getting it in batches. Like think of a hospital, for instance. In medical domain, we get a certain amount of data in the beginning. We keep getting data. From the first visit, we get certain data. Second visit, we get certain data. So it's a very dynamic, most of the data sets are dynamic. Usually the things that we use in academia are kind of these static data sets where you have access to a specific train set, a specific test set. But in most cases, there's nothing called a train test set. You have to create your own train test splits, and that's why cross-validation will give you like a randomized way of getting the best possible model. Any other questions? Yes.
How do we use the validation set to for hyperparameter QC?
I'll talk about that. That'll be the first thing I'll talk about. But just before that, there is a visualization tool that does this kind of that shows specifically for neural networks. I think I had that open as well. So you try to play around with this tool. It's a very simple tool based on a very simple number of parameters, neurons, and number of hidden layers, where you can increase, decrease your hidden layers. You can start training your model and so on. You can also have like different data sets to start with to see how you can classify between your data. So it's a very simple module. It runs on the browser. So you should be able to try to understand what is happening. So in this case, right, within this neuron, it's a very vertical classifier. So it's just using this as the classifier. In this case, it's using a horizontal classifier. And this is one way of thinking about a neural network. The first layers are doing a very simple linear classifier. Then the output of that is now being classified again by the second neuron, second layer. So you'll have this kind of a better way. Let me increase the regularization a little bit. Oh, this is the maximum. Maybe it trains. Yeah. Not this. Okay, this is much better, right? So this is the second layer. Essentially, it takes the outputs of your first layer and classifies on top of it again, over and over again. And if you have multiple hidden layers, that is essentially what it's doing. So you're creating this kind of a two classifier setup in a nonlinear fashion, just based on number of classifier in your first layer. So just play around with this tool. It should hopefully help you try to understand neural networks. I think in lecture 21, 22, we'll discuss more about something called explainability within deep neural networks. We'll revisit this kind of results again. Right. So hyperparameter search. So hyperparameters, till now we talked about parametric models. Parameters are whenever we say parameters, they are the learnable parts within a network, within a model. So W and B were our parameters. This is something we learned across epochs with millions of data points. But then there are certain hyperparameters that we need to use. For instance, in gradient descent, when we were doing that weight update, right, there was a W minus alpha into dou L by dou W. The alpha at the time we just said was a step size or a learning rate, and I did not comment anything more on that. That is a hyperparameter. That is something that I set in the beginning itself without having access to seeing the data, without doing anything, doing any of the learning framework itself. So anything that is set by human beings before learning starts is something that we are going to call as hyperparameters. So in k nearest neighbors, the number of points we use in order to find the distance between the test data and the training data, we have to set this beforehand. We need to say that I'm going to look at the 5 nearest neighbors in order to make a decision. So that number 5 is a hyperparameter that I set. Hence, that would be a hyperparameter. In support vector machines, for instance, your capital C, which we were using for regularization, was another hyperparameter. I believe there is one question within your homework where you'll see how that hyperparameter is going to affect the shape of your classifier. Right? So that is another hyperparameter. In neural networks, number of hidden layers, learning rate, there are multiple ways of multiple hyperparameters that we are using, and we have to make sure that these hyperparameters are not something that is going to adversely affect our training data set. The way we are going to use or learn these hyperparameters is via cross-validation, or at least one way of using it is via cross-validation. So, cross-validation helps determine hyperparameters. So let's say that we start off with this data set here, where in the first iteration, our entire training folds is going to have one test fold. I'm just going to use this as a test fold in my first validation. I'm going to do it across, in this case, we're doing 10th iteration, so let's say 10-fold cross-validation. At every single instance, I'm going to get E1, E2, E3, and E10, which is going to be my error, right? So this is a standard cross-validation process in order to get my outputs. For every single fold at this point, I'll have some kind of an evaluation error. So for k-fold cross-validation, this is the procedure. This is something that you have seen before. Every single cross-validation, I can now choose a different parameter. That's the simplest way of putting this. So let's say I have nearest neighbors. I'm using nearest neighbors algorithm. In the first k-fold cross-validation, I'm going to use 5 as my k. In the second one, I'm going to use 3. The third one, I'm going to use 4. So I can construct different hyperparameter-based models at every single iteration or at every single fold, and use that as and use the error as a way to choose the best model or to choose the best hyperparameter. So this is a brute force approach for finding what the hyperparameter is. In some cases, it is going to be different. For learning rate, for instance, you can schedule your learning rate. You can say that across the first 50 epochs, I'll have my learning rate as 0.1. The next 20 epochs, I'll have my learning rate as 0.01. And this is a very popular strategy in neural networks, the learning rate scheduler, for doing the hyperparameter selection. In other cases, cross-validation is another way of using or choosing the best hyperparameter that is possible. There's no one solution for choosing the hyperparameter. Depending on which one you're trying to choose, you can try different ways. But the most brute search approach that you can do in order to get the best hyperparameter is via cross-fold, k-fold cross-validation. Any question in what that each of these means in terms of hyperparameters? Or what a hyperparameter is? The next is we'll start with the performance evaluation metrics. The first one we'll be looking at is accuracy. So accuracy is very straightforward. It's just the number of correctly labeled samples divided by the total number of samples, which is, in this case, you're going to search for the true and true, and the false and false. That means they're correctly predicted. Hence, accuracy is going to be 7 by 10 in this case. The problem with accuracy is that when some data set is unbalanced. So what do I mean by unbalanced? So here there's only about 10 data points. Let's say there were 1 million data points, out of which 90,000 of the data points were true, and about 10,000 were false. So if my model learns to predict everything as true, it starts off with an accuracy of 90%, right? So a trivial solution itself gives me a 90% accuracy. So it's not a good, accuracy by itself may not always be a good measure to see how good your model is working or not. In that case, we have access to other performance evaluation metrics, which are these kind of true positives, false positives, true negatives, and false negatives. The words themselves describe what each of these metrics mean. So if your output is positive and it's successfully predicted as positive, then that means it's a true positive. Maybe the next slide is better for looking at this. So let's just look at the right-hand side table over here. So the first output, your answer key was a false and your answer was a true. Clearly it's a mistake. Even accuracy knows that this is incorrect. But if we divide this based on the TP, FP, TN, and FN, you'll see that the answer key was a negative. So the actual output is a negative, while your method is actually telling you that it is positive. So it is what we call a false positive. So your method, your algorithm is telling you that this is supposed to be true or positive, while it is actually negative, which makes it a false positive given by negative, but mistakenly accepted. Look at the next one. It's false and it's a false. So it's a negative to start off with. Your algorithm correctly predicted it's a negative. Hence, it is a true negative, which is good. Your algorithm did well. Accuracy knows this. But in terms of classifying, in terms of the fourth thing, it is a true negative. T and T, it is your actual output is supposed to be true. The label is true. Your answer is also true. Hence, the output is a true positive, which means that it's positive and it is successfully accepted. Let's look at FP. Where is FP? Let's look at the last one. We are, which is, actually we did FP, right? FN is something that we did not do. Yeah, FN, T and an F. So your output, your actual label for your data point is true, but you are predicting it as a false. That's essentially a false negative. So it's positive, but mistakenly rejected. So we, instead of just looking at whether the output is correct or incorrect, you look at the label as well in order to make the decision how good or incorrect your label is. Now this can be very important because think about something like a false negative in a medical setting, right? So you're classifying whether there's a disease or not within a particular image, within a particular CT scan. If the disease actually is present, if there's, let's say, a nodule within your lungs, but the scan says false, the diagnosis says false, it can be very problematic. So the reason we have access to all these different performance evaluation is in that in some instances, FN is catastrophic. You never want a false negative. It's fine if you have a few FPs, for instance, where it's false, but it says it's true. So that just means that you need to do more diagnosis. Again, it's not ideal, of course, but it's much worse to have something like a false negative, where you do have a disease, but it's not classified. It's not, its scan does not show it, or it was not diagnosed using the scan. So that's why all these 4 different metrics can be very important in different scenarios and quite useful there. Any questions about the 4 different metrics? Yes.
Will you do one versus all?
That's the easiest way to think about it, yes. One versus all. There's also a many versus one method as well. We'll discuss that when we come there. But for now, that's the easiest way to think about for a multi-class setting. Any question? So then, if we don't have access to that, then let's say I have other kind of metrics, precision, recall, F1 score. All these are just a combination of your TP, FP, and FN. Essentially, what you need sometimes is precision. So how many selected items are relevant? You don't care about how many false negatives there are. In such cases, you're only looking at precision. So on the left-hand side here, it tells you that precision is a good measure when the cost of FP is high. So when your false positives are very high, in other words, you have an output and a label which is negative, but then you're accepted it. If that part is very high, then precision is something that you should be looking at. Recall, on the other hand, is the opposite. If you see the numerator is the same, it's still a true positive, but in the denominator, you're going to have a false negative. So recall is a good measure when the cost of Fn is high. Depending on your methodology, your algorithm itself, sometimes you might have a good result, sometimes you might have or sometimes you might always have positives, while sometimes you have always have negatives. In that case, you need both precision and recall to see what kind of performance your model is outputting. Instead of looking at 4 things, right? So here, if you just give it to someone and say, help me try to select a model by looking at these 4 metrics, it might be difficult because you can't always make a decision based on 4 different numbers. But if you can successfully combine them into functions, might be better. So precision, recall, and F1 score are ideally just a functions of TP and FN, FN and FP actually, depending on which an application needs more, which an application is more sensitive to. That is when we use either a precision or a recall. So this is more of an example for precision recall. I don't know if we have the time sufficient enough to do this. I had hoped that we'd be finished doing this by now, but unfortunately I was not able to come to ROC. It's about like 3-4 slides away. But ROC is something that is there within your the homework itself. Oh, sorry. I don't know why this keeps happening. This happened last time as well. But ROC is something that is there in your homework. You have to create your own function. Unfortunately, I was not able to finish doing it today. We'll complete it on Wednesday. That's the first thing we will complete. But I believe it's only part of a question. You have to create your own function to do ROC. You can test and try it using scikit-learn. You'll get access to ROC curves in scikit-learn, so you should be able to verify whether your function is correct. But in the homework itself, we want you to create your own ROC function to see the outputs. I'll cover that the first thing on Wednesday, but it shouldn't be too difficult to do it even when you do it on Wednesday. That should be the end of the class, and for some reason my PowerPoint keeps disconnecting.